Hi. So this question, I believe these questions come from your roadmap. So a student had questions about numbers 10 to 13. So dealing with an electron between charged plates. And it asked a whole bunch of questions about that. So we'll work through this kind of one question at a time. It is kind of a good review of work energy theorem and moving in uniform electric fields. So here we have an electron between two oppositely charged plates. Try to draw this straight. So here's a negative plate. Oh dear. It's a little wobbly, sorry. Here is a positive plate. So we know the distance between these plates is 6.50 millimeters. So we put the electron between these plates, okay, and it says, so the electron will travel towards, if we think about just the nature of the charge on the electron, so the electron has a negative charge, it's going to move away from the negative plate and towards the positive plate. So the electron will travel towards the positive plate. And then if we think about the electric field, again, electric field is the direction a positive test charge would move, and that would be the opposite direction because a positive test charge would move that way. So the red is the direction of the electric field. The electron in blue is going to move towards that positive plate. That's number 10. In number 11, it asks for the voltage between the plates. We have a whole bunch of physics equations, but the one that we kind of want to deal with here is this voltage is a change in energy per unit charge. Now this E is not electric field, okay? This is different. This is not electric field, this is a change in energy. So voltage can change the energy of something with charge. So when I can rearrange this equation because I want to find, actually I don't even need to rearrange it, I want to find the voltage. So I know my change in energy of 8.25 times 10 to the negative 18 joules. I'll put that in my calculator, 8.25 times 10 to the negative 18 joules, and divided by the charge on an electron. Now that's in my formula, on my formula sheet, it's 1e, so 1.6 times 10 to the negative 19. And I get 51.6 volts. So that should be A. So when I do that calculation, I get 51.6 volts is the voltage between those plates. Also asked me for the strength of the electric field. So I know the voltage. I probably just go maybe one step further. So I know electric field is my voltage over my distance. So my 51.6 volts divided by my distance of 6.5 times 10 to the negative 3 meters is 7,933. So 7.93 times 10 to the 3. Sorry, I have a really big fat like iPad crayon that makes it hard to draw right now. I have like a smaller pen coming, but that's C. That's supposed to be C. So that's kind of those first couple. So those are really just using those electricity and magnetism formulas. There is a difference again though between electric field, which is a vector, and then change in energy. And sometimes this change in energy is missed, but the change in energy is a really useful one. So we're also going to look at that very last one, so 13 now. 13 now, it asks for the speed acquired by the electron as it reaches the positive plate. So it says it starts at rest and then accelerates and gains that much energy. So this is a type of question that sometimes we can use kinematics. What am I doing there? So sometimes we can use kinematics to solve these questions. But we can also do it a different way using that work energy theorem. And that's kind of, I think, what this question's getting at, is we do know the change in energy of that electron. So if we think about the electron here, the kinetic energy is 0 if it starts from that plate, or I guess it's starting from rest, so it has no kinetic energy. And then when it reaches that positive plate, it is going to have a certain amount of kinetic energy. So that there's a change in energy of that electron, and it's really going to be equal to that final kinetic energy. That's kind of what's going to happen to that electron. So it gains energy, there's a change in energy because it's moving through a uniform electric field, and then it's going to have a final kinetic energy. So we know that that change in energy is all kinetic. So we have 8.25 times 10 to the negative 18 joules. And that's equal to all kinetic, so 1/2 mv squared. We're trying to find v, so then we just kind of rearrange this equation and solve for it. We do have the mass of an electron on our formula sheet. So 8.25 times 10 to the negative 19 times 2, because I need to multiply by 2, divided by 9.11 times 10 to the negative 31, because that's the charge on an electron. And then I square root it. And I get none of those answers. Initially at rest, accelerates towards one of the plates, gaining that much energy, 1/2 mv squared. Did I have the mass of an electron wrong? 9.11 times 10 to the negative 31. Okay, so let's try that again. 8.25 times 10 to the negative 18. It's joules of energy. It's a change in energy. It's all kinetic, so times 2 divided by 9.11 times 10 to the negative 31, and then square root it. Oh, now I get a different answer. So I get C. I think I did something wrong with my calculator. So I get 4.26 times 10 to the 6 meters per second. Questions like this, if you do see them, there are ones that you should be able to rule out. Like D is a bad answer, because that's faster than the speed of light, which is 3.0 times 10 to the 8. So things can't go faster than the speed of light. If they do, something's gone very wrong in the universe. But yeah, so that's how you do questions number 10 to 13. If you do have more questions about this, just post it kind of in this stream, and I'll try to respond to those as well.